Yes. I need my umbrella. Hello, everyone. It's great to be here today on stage. You'll probably be wondering what the guy with the umbrella, and I wanted also to wear sunglasses, is doing on stage. Well, these two accessories represent total uncertainty of weather. One moment, the sun is shining, the next, it's raining. The weather is chaotic, fickle, and often hard to predict. It's a challenge that has fascinated scientists for centuries. And that very challenge is the core of my work. As the founder and CEO of AIDAQ, I am dedicated to the development, the data, and the question of how we can use AI to radically redefine metrology as a science. My goal is to get this uncertainty under control through machine learning. I will put the umbrella away now. Let's start with a little story. Who here has had to run for cover from a sudden downpour, even though your weather app promised sunshine just 5 minutes ago? Yeah, me too. We all know this problem, and that's a nowcasting problem. And that is exactly where our work begins. And why it is so critical. The energy transition is a fantastic development, but it makes us also dependent on fast, precise weather forecasts. Wind and sun are unstable. To guarantee the stability of our power grids, we need forecasts by the minute. Barbara just talked about it in the lecture before. Traditional forecasting models, which are based on complex physics, are simply too slow for this. They are like a huge tanker, incredibly precise but slow to maneuver. They solve complex equations that describe the flow of the atmosphere and thermodynamics. A full forecast run can take hours. By the time the data is processed, the actual weather can already look completely different. And that is exactly where our solution comes in. With the Nowcast AI project, we are breaking with this approach. We say weather forecasting is not just a physics problem, but a pattern recognition problem. We don't ask what forces are acting on this cloud, but rather, what do the last 10 cloud images have in common, and what will the next one look like? Our project, funded by EuroHPC, is a proof of concept to prove exactly that. We are focusing on solar radiation, an area that is often ignored by the big AI weather models. But for us, it is crucial. Let's take a closer look at the difference. On one side, on the left side, we have numerical weather predictions, NWP. These are the traditional models. They are the result of decades of scientific work and solve complex differential equations that represent the dynamics of the atmosphere. This is science at the highest level, but it is incredibly computer intensive and takes a long time to process the newest data. You could say it's a first principles approach. It has to be done for each forecast day by day. Our answer is AI weather forecasting. You see it with the left globe rotating very fast. We see weather data as a kind of video sequence. Our model learns to generate the next frame from a series of radar satellite images. This is essentially an image-to-image problem, as we know it from the field of computer vision. Imagine this. A computer gets thousands of satellite clips. It sees how clouds form, how they move, and how they disappear. The system learns to recognize patterns in the data without having to calculate the underlying physical laws. That, simply put, is the principle of our work. We use architectures like UNet, which are ideal for processing image data. A UNet consists of an encoder, it's the left side, that extracts the important features from the input image, and a decoder that uses these features to create the forecast image. The connection between the encoder and the decoder, the U-shape, that gives its name, it allows the model to learn both the rough, large-scale patterns and the fine details. Working with AI means finding complicated patterns in historical data that human scientists may not be able to recognize. To enable such a revolutionary forecast, we need one thing above all: data. A lot of it. Our data set is petabyte-sized and multimodal. That means we feed our model a mix of information that has different spatial and temporal resolutions. I will explain now. Satellite data from EUMETSAT gives us the big picture of clouds and weather fronts. You could say they provide the global view of the weather situation. Here, we work with images from geostationary satellites. The newest generation, METEOSAT 3rd generation, already provides us experimentally with images with a resolution of 1 kilometer per pixel every minute. This data is key to capturing the movement of large weather systems. Radar data from the DWD, the German Weather Service, for example, gives us high-resolution information about local rainfall. Here we are talking about an extremely fine resolution of 1 kilometer per pixel and a frequency of 5 minutes. These images give us a near real-time snapshot of where rain is falling. And by the way, they are essential for recognizing the local storm cells that left us standing in the rain. The outputs from traditional NWP models give our neural network additional context. These models work on a coarser resolution of about 2 to 7 kilometers and provide forecasts for a period of up to 24 hours. This helps the AI to understand the large-scale atmospheric dynamics that might not be visible in any image. They are like the collected knowledge of an experienced meteorologist that we give the model as a foundation. And now, most importantly, measurements from hundreds of ground stations which serve as our ground truth. These are only point-based data, but they are extremely precise. Measurements like solar radiation and temperature often come in every 10 minutes. This is unique. It allows us to specifically train on forecasting solar radiation, for example. These data points from the ground are our source of truth. Without them, the model would not be able to refine its forecasts and precisely predict solar energy, for example. The ground stations give the AI model feedback on how good it actually was. Processing these massive amounts of data is only possible with a distributed GPU infrastructure. This is where HPC comes in. It means high-performance computing. We use PyTorch Lightning and MLflow for our training. This is the basis of our MLOps strategy. MLOps, or machine learning operations, is critical because it ensures that our models don't just work once. They must be reproducible, scalable, and sustainable. It's about managing the entire life cycle of an AI model, from data provisioning to training and validation to deployment. Thanks to this power, we achieve a spatial resolution of 1 to 4 kilometers and a temporal resolution of 1 to 2 minutes. This is a level of detail that would be very difficult to achieve with traditional nowcasting methods. And it enables completely new application scenarios. And what is the point of all this? The answer is very simple. We create real value. Weather is just the foundation of what we are doing. We turn weather into real business insights. And now see my example from the energy sector. Imagine an energy trader who wants to offer his solar energy on the market in the best way possible. If a cloud suddenly moves over the PV system, the performance drops. That costs money. Our nowcasting forecast warns him about exactly this situation. It can tell him that production will drop by 30% in 15 minutes. This allows him to act in time to minimize costly balancing payments. But this is about more than just finances. It's about grid stability. Barbara was talking about it before. Imagine our power grid as a seesaw. On one side is production, on the other is consumption. As long as the weight on both sides is the same, the seesaw remains stable. But what happens when a thick cloud suddenly moves over a huge solar plant? As I said, production drops abruptly. The seesaw tilts. And what if no one sees the problem in time? There is a risk of blackouts that could paralyze our entire infrastructure. To maintain balance, electricity must be fed in from other sources immediately, such as from gas power plants or batteries. This is expensive and has to happen extremely quickly. Our high-resolution nowcasts give grid operators the time to plan these measures proactively. They can keep the seesaw stable before it even starts to tilt. Without such precise, fast forecasts, it is impossible to operate a stable grid with such a high proportion of renewable energy. This is no longer a theoretical concept. It is a critical tool for grid stability and profitability. In summary, AI forecasting is improving all the time. Just look at how much the quality of forecasts has improved in the last 5 years. You don't have to read every single text here. It shows the different weather models, or AI weather models, and by the years, the quality gets much, much better. But be sure, classic NWP, the physical modeling, classic weather forecasting remains largely a matter for national and multinational weather services. But we will see many, many new models and approaches using AI. Nowcast AI, our project, is an experimental test project that pushes the boundaries of what is possible. AI weather forecasting is not a revolution that will completely replace the old methods. Instead, it is a huge evolutionary step. And here is the best. Both the traditional physics-based models and our data-driven approach will benefit from each other. The new AI models will learn from the historical data of the physics-based models, and the traditional models can be improved with the insights gained from AI. We are at a fascinating point. AI is not just a tool. It's a co-pilot. It helps us to understand the chaotic and complex atmosphere. This will enable us to build a more resilient and sustainable future. Research never stands still. We are seeing rapid development. Models like Google's MatNet or GraphCast show that AI is revolutionizing the entire field of weather forecasting. From minutes to 10 days in advance, the models are becoming faster, more accurate. They can be created with less infrastructure. What was once reserved for supercomputers can now be handled with smaller infrastructure. Another important point is interoperability. We are working to design our models so that they can be integrated into existing systems. This makes them a valuable addition to traditional models. We are at the beginning of an exciting development, and I'm thrilled that we can be part of it. But one more thing, and I come back to my umbrella. Even with all technological progress I've presented, the next weather app will probably still leave us standing in the rain at some point. Because even if we are getting closer to understanding the weather, we are still just observers. The nature has its own laws, and some things will hopefully remain a small secret for AI forever. That was my 2 cents. Thank you very much for your attention.